All right, guys, sorry about that. Wasn't paying attention at the time, got cut out. So I believe we're on client. So the client is the receiver of that information. So basically, what happens here is the server takes a packet, which is the message, right? The message that needs to be sent. Brakes were applied. That's the message, right? Takes that packet and shoves it out onto the data backbone, which is the two wires that every single computer is hooked up to, the same two wires, right? Shoves that packet out onto the backbone, and then a client gets to choose whether or not it wants that packet. Now, it chooses by basically being told that it needs that information. So, in the descriptor, which every message has a descriptor in it, it understands, it reads the descriptor and says, oh, I need that message, or oh, I don't want that message, right? So every single message that every single computer makes is shoved onto this wire. And we'll talk a little bit about how it does that later, but it gets shoved out onto this wire, right? And then a client or another computer can choose whether or not it needs that information. And if it does need it, then it takes in the whole message. If it doesn't need it, then it just ignores it. And so on and so forth. So how this works is timing. Everything has to be perfectly timed, right? So right off the bat, one computer has to be able to send out a message in time with every single other computer in time. Because if one computer is running, let's say, I don't know, off beat, right? So every other computer is sending out a digit at the exact same time, and one of them is running just off, just half a beat, then it's going to completely destroy all communications between every single module. In fact, this happens. It happens quite a bit. So an internal resistor inside of these modules can burn up and short out, and it starts bouncing a message back on that wire, which is off beat. And what that does is it causes a miscommunication. So when a computer is supposed to be reading a 1, it may be reading a 0, going, what the hell do I do with this? This isn't a message I need. And it just shuts down the entire unit because nobody knows what to do. So everything has to be timed perfectly, right? That's step one. Once everything is timed, then all you need to know is who's most important. And we're going to talk about who's the most important later, but you need to know who's most important because whoever's most important gets to send out the first message, right? If you're the most important, you get to talk first. That's just the way it goes. Whenever you have a group full of people inside of one room, whoever's the most important gets to talk first, right? Or the loudest, in which case they're usually the dum-dum that's sending the message that's offbeat, right? Otherwise, it's the most important person. So anyway, let's move on. The most important person talks first. They are the server. Everybody else is a potential client if they choose to determine that the packet that is on the backbone is important to them. All right, so let's give a visual representation here. All right, so this will be a truck is what this is. You got a fuel injection ECM, an engine ECM, a transmission ECM, a chassis management ECM, a dash display, ABS ECM, and a collision warning ECM. So all these different ECMs are communicating on the data bus highway. And I want you to view it exactly like that, a highway, a river, whatever it may be, right? Because that's what it is. They're all on this same two wires, the same communication area, right? So anyway, let's say something happened. So we have a collision warning here, right? Everybody's seen the new fancy cars. If somebody walks in front of you, they stop. Trucks have that too. So somebody walks out in front of you, so this collision warning here is going to send out a signal. It's going to be an important signal, right? Because stopping the truck before killing somebody is going to be a lot more important than the message being sent by the transmission to, what temperature it's running at. Now, is temperature important? Yes, but it's not as important as getting that truck stopped in time. So the collision warning ECM is going to send out that message, and everybody else is just going to shut up. Because currently, at this moment in time, collision warning is the most important guy in the room, right? He's the most important. He's going to send out that message saying, hey, everybody, shut your shit down. We're about to hit somebody. And everybody's going to listen. All these other ECMs are going to pick up his message. He's going to send out 0011, 00011. Every one of these guys is going to pick that up. Immediately, the dash display, right? It's going to bring up a nice big flasher saying, hey, we're slowing down to let the driver know what's going on. The ABS guy, he's going to potentially apply the brakes all by himself, right? Chassis management, that's going to be your brake lighting system. So as soon as your brakes are applied, you have to have brake lights on. So those are going to be turning on. Your engine ECM, it doesn't want to be revving up at 5,000 RPM while the brakes are being applied, right? So it's going to back off all the RPM. Well, if the RPM's dropping down, the fuel injection's going to drop it down. So this entire unit communicates all in one because this one unit said, hey, listen here, guys, this is what we're doing, and I'm important, and that's it. And everybody else listened, and everybody else shut it down because he sent one line of zeros and ones out onto the data highway. So now that we're looking at this data highway, right? Currently, we're looking at what some OEMs originally actually exactly what they did. This was wire 1, this was wire 2, and they were all connected into each individual ECM. Every ECM was considered important, and every ECM talked on the exact same 2 wires. Very effective use of communications. However, it gets better. So a couple years later, if you didn't already have this, you moved into what could have been called a gateway system or a hub or spoke wheel design. A lot of different names depending on your OEM, but it's a different type of controller area network or CAN bus communications, right? So you have all of your important ECMs, right? These are all connected on the same 2 wires. Every single one of them, instrument cluster, cab, CECU, body controller, it didn't really matter. They're all important. They all talked on the same 2 wires. And then you had some subcategories for, like, example, your variable geometry turbo, right? Does the turbo need to tell the instrument cluster what's going on? Not necessarily. Does it need to tell the cab? No. Body? No. Chassis? No. Nobody cares what the VGT turbo is doing except for the engine ECM, right? So the engine ECM is going to receive modules from the turbo. It's going to make a smart decision on what's going on. So let's say the turbo sent a code saying, hey, I'm broken, something's going wrong, we need to shut down the truck. The ECM for the engine is going to make that decision on whether or not to actually shut down the truck. The VGT has no say over these other modules. They do not communicate with the other modules. They do not send out zeros and ones to talk to the other modules. They just send out zeros and ones to talk to the engine ECM. If the engine ECM determines, hey, this is a message I need to pass on, then it's going to send out its own list of zeros and ones saying, hey, let's shut this down, right? So on and so forth. Now, there's many subcategories that could potentially show up in a spoke wheel design. This is a very simplistic example, but let's look at something more like this, right? So back to the ECM right off the bat. Here's our ECM. Here's our communications with all the other modules. Right here, though, are all the private modules or the sub-modules. They do not communicate directly with any of this stuff over here. They only communicate with the ECM. And for good reason. Nobody cares what the upstream NOx reading is except for the ECM. Now, there might be possibly a dash that reads out NOx reading. Why? I don't know. Customer add-on, something like that. But that's going to be sent from the ECM, not from the sensor itself. So this is the spoke wheel design. All this unnecessary information, at least according to everything over here, doesn't get read over here. It only reads to the ECM, and then the ECM determines, hey, should I pass this on or not? So the main communication, the public network, oh, excuse me, I need to explain public and private network. So this would be a private network because it only communicates with the ECM. So everything here is a private network. Everything here is a private network. But if you get into this, all of these different modules right here that are communicating, ECM, CECU, transmission controller, driveline, I mean, all of this different stuff that's all on the same network, that's called the public network. None of the private signals communicate on the public signals. When you plug in and you want to talk to a unit, you're going to actually plug into this diagnostic connector here, which goes to the public network. Now, depending on what software you choose, decides who you're going to actually talk to. So if you want to talk to an Allison transmission, you're going to upload the Allison software, and it's going to come in here and it's going to grab all the information off of this Allison ECU, and it's going to put it outread it on your computer. If you want to talk to the ECM, you may go get, let's say, Cummins software, and you're going to hook up and it's going to grab all the Cummins information and communicate it right here, so on and so forth. Anything on the public network you can talk to directly using the correct software. If you want to read Knox upstream, though, you cannot use Knox upstream software. You have to use Cummins software and then read the Knox upstream data. That's the difference between public and private networks. All right, so communications. Communications are all on two wires, and these wires are twisted right here. So before, remember how we talked about a magnetic field is created whenever you have a coiled wire, right? That's exactly what they're doing. They're coiling these two wires together. That way it creates a nice magnetic field around the outside of those two wires. Now, what's the advantage of that? Well, basically what it means is if at any point in time we have another wire running beside these two wires, no signal is going to be able to penetrate and start jumping over into these two wires. It's got an electromagnetic shield blocking them because of the twisted pair. And that's a very good thing because we're dealing in zeros and ones, right? We can't have any miscommunication whatsoever. Otherwise, we might be braking when we need to be accelerating or so on and so forth. So anyway, we twist those wires together. It creates a nice magnetic shield around the outside of those wires that no other signal can penetrate through. So you can now officially put these two wires inside of a harness of 500 other wires and not have to worry about a miscommunication because a signal jumped from one wire to another. So these two wires come in, they're twisted pair all the way up to each and every single individual ECM, and then they come into the end here, and these are called terminating resistors. So basically what a terminating resistor is it's a resistor at the end that eats up the signal. So let's say this ECM sent out a message, right? That message is coming along these two wires and it gets down here and it eats all that signal up after, everybody's had a chance to grab it if they chose to. If they chose to grab the message, then it reads the message. Otherwise, after it gets all burned up inside of these terminating resistors, gets rid of that message. Because if you don't get rid of that signal, what's going to happen to it? Well, that signal is going to come to the end of the wire and then start to bounce back, right? Well, we can't have that. We can't have a bounce back of signal because if we get a bounce back of signal, then the next message that gets sent from this ECM is going to interfere. And now we have conflicting signals. So we need something to eat up those signals at the end of the wire, and that's where our terminating resistors come from. So the backbone itself is a twisted pair of wires with twisted wires going to each and every single ECM and terminating resistors on the end to eat up the signal. That's it. That's the whole backbone. All right, so can high and can low. The difference in the wires. This is the yellow wire versus the green wire. So if we go back to our previous slide here real quick, can high, can low. That simple. Can high, can low. That simple. Now, so why do we need two wires? See, now we talked about having multiple wires can increase speed of signal, but that's not what we actually use it for anymore. Now we actually use it as a redundancy or a repetitive message. That way a computer can verify that it's receiving the right message. If there's ever a fault on the system, it knows there's a fault on the system because the two messages do not match. That's why we have two wires. Also, the twisted pair is nice for electromagnetic repulsion as well, right? But finally, another thing we need to understand about these two wires is you'll notice every other circuit we look at, the wires have a power and a ground supply. There is no power ground supply. It is literally just two wires hooked to themselves through terminating resistors and ECMs. No power, no ground. Important to understand that. There's no power and no ground. They are just simply talking to each other until they get a message burn up at the end. All right, we're about out of time, so I'll shut this video down and we'll get another one going here in a little bit. All right, see you guys later.